Today we're doing section 2.2, the inverse of a matrix. The inverse of a real number a is denoted by a inverse. For example, 7 to the negative 1 or 7 inverse would be 1/7. And 7 times 7 inverse equals 7 to the negative 1 times 7, which equals 1. An n by n matrix A is said to be invertible if there is an n by n matrix satisfying the following. So when you multiply the two together, you'd get the identity matrix. Fact: if A is invertible, then the inverse is unique. The inverse of A is usually denoted by A inverse. Not all n by n matrices are invertible. A matrix that is not invertible is sometimes called a singular matrix. An invertible matrix is called a non-singular matrix. Theorem 4. Let A be the following matrix. If AD minus BC does not equal 0, then A is invertible. So A inverse would equal 1 over AD minus BC times D negative C negative BA. So what you do is you interchange these and this diagonal and take the negative of this diagonal. If AD equal minus BC equals 0, then A is not invertible. Theorem 5. If A is an invertible n by n matrix, then for each vector B and Rn, the equation Ax equals B has a unique solution. X equals A inverse of B. Let's look at example 1. Use the inverse of A to solve the following. So that should say inverse. Negative 7x1 plus 3x2 equals 2, and 5x1 minus 2x2 equals 1. So here I have the matrix negative 7, 5, 3, negative 2. That would be my A. Then my vector x, and this would equal B. So here I have A, X, and B. So first we're going to find A inverse, which would be 1 over 14 minus 15 times negative 2, negative 5, negative 3, negative 7, which equals 2, 5, 3, 7, because this would just be negative 1. So then X would be A inverse times B. So that would be 2, 5, 3, 7 times 2, 1, which would equal 7, 17. So x1 would be 7, x2 would be 17. Theorem 6. Suppose A and B are invertible. Then the following results hold. A inverse is invertible, and A inverse inverse equals A. A is the inverse of A inverse. AB is invertible, and AB inverse equals B inverse times A inverse. And C, A transpose is invertible, and A transpose inverse equals A inverse transpose. Elementary matrices. Elementary matrix, obtained by performing a single elementary row operation on an identity matrix. So let's look at example 2. We have E1 equal 1, 0, 0, 0, 2, 0, 0, 0, 1, E2 equal 1, 0, 0, 0, 0, 1, 0, 1, 0, and E3 1, 0, 3, 0, 1, 0, 0, 0, 1. And we have A being ADG, B, EH, CFI. E1, E2, and E3 are elementary matrices. Why? So if I look at E1 times A, this would just be my one operation that I do. It would be A, B, C, 2D, 2E, 2F. So that would be my one operation. 2D, 2E, 2F, and then G, H, and I. So I'm just multiplying the second row by 2. If I look at E2 times A, I'm just interchanging these two rows to get my elementary matrix. So A, B, C would stay the same. G, H, and I would come up here. And then I'd have D, E, and F down here to get my identity matrix. And then the last one, E3 times A. I'm just taking 3 times the first row and adding it to the last row. Also note here, and I'll move this up, if an elementary row operation is performed on an m by n matrix A, the resultant matrix can be written as EA, where the m by n matrix E is created by performing the same row operations on the identity matrix. Let's look at example 3. Find the inverse of 103,010,001. So we need to find the inverse of this. So E3 is that, so we need to find E3 inverse. And it would just be this would be negative for its inverse. So elementary matrices are invertible because row operations are reversible. To determine the inverse of an elementary matrix E, determine the elementary row operation needed to transform E back into the identity matrix and apply this operation to I to find the inverse. So if I wanted to get this back to the identity matrix, I would just multiply this by -1 and add it to this, and that would give it to me. And now let's look at example 4. Let E1, E2, and E3 be as they were before, and now A is 1, -3 half 0, 0, 0, 1, 0, 1 half 0. Find E3 times E, 2 times E1 times A. So the first thing we're going to do is we're going to find E1 times A. So the first thing we're going to do is find E1 times A. When I multiply through, I would end up getting 1, negative 3, 0, 0, 0, 1, 0, 1, 0. Next, we're going to find E2 times E1A. So E2 is 1, 0, 0, 0, 0, 1, 0, 1, 0. When I go ahead and multiply those, my resultant matrix would be this. And now I'm going to go ahead and multiply E3 by E2, E1A. So E3, and you should already know what you are going to get. And this is going to be multiplied by 1, 0, negative, or 3, 0, 1, 0, 0, 0, 1. And since this is the inverse, you're going to get the identity matrix. So E3 times E2 times E1 times A equals the identity matrix. So therefore, E3 times E2 times E1 times A inverse equals the identity matrix times A inverse. So E3 times E2 times E1 times the identity matrix equals A inverse. Theorem 7. An n by n matrix is invertible if and only if A is row equivalent to the identity matrix. And in this case, any sequence of elementary row operations that reduces A to the identity matrix will also transform the identity matrix to A inverse. The algorithm for finding A inverse. Place A and the identity matrix side by side to form an augmented matrix. Then perform row operations on this matrix, which will produce identical operations on A and I. So by theorem 7, AI will row reduce to A inverse, or A is not invertible. Example 5, find the inverse of A if it exists. So what we're first going to do is we're going to set this up as AI. So A being 2, negative 3, 0, 0, 0, 1, 0, 1, 0. My identity matrix, if you want, you can put a dash line through. 0 or 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. And now what you do is you perform elementary row operations until this becomes the identity matrix, and this would give you A inverse. Okay, so the first thing I'm going to do is I'm going to take 1/2 of row 1, so that I would have a lead in 1 here. So that would give me 1, 0, 0, negative 3, 0, 1, 0, 1, 0. Since I did 1/2 to this row, I have to do 1/2 to this row, so it'd be 1/2, 0, 0, 0, 1, 0, 0, 0, 1. Next, I'm going to interchange row 2 and row 3, since that has a middle 1. So I'd have 1, 0, 0, 0, 1, 0, negative 3, 0, 1, and 1/2, 0, 0, 0, 0, 1, 0, 1, 0. And the last thing I'm going to do for this is 3 times row 1 plus row 3. So I'm going to take 3 times row 1 and add it to row 3. So row 1 is going to stay the same. Row 2 is going to stay the same. 3 times row 1 and add it to row 3 will give me 0, 0, 1. So 3 times row 1, adding it to row 3 would give me 3/2, 1, 0. So A inverse would be 1/2, 0, 3/2, 0, 0, 1, 0, 1, 0.